So we have part one of complex analysis practice final exam. So let's begin. Let f be holomorphic on the disk. Absolute value of z is less than 3. And suppose modulus f of z is less than or equal to 1 over 3 minus that absolute value of z. For all absolute value of z is less than 3. Prove that for part A, B, and C respectively. Part A, prove that for every 0 is less than r is less than 3, modulus of fn of 0 is less than or equal to n factorial over r to the n times the quantity 3 minus r. For part B, find the value of r that gives the best bound. And for part C, deduce an explicit asymptotic upper bound for that modulus fn of 0 as n approaches infinity. So this is Cauchy theory and estimates problem. So by Cauchy's estimate, if f is holomorphic on absolute value of z is less than or equal to r is less than 3, then this absolute value or modulus f of n of 0 is less than or equal to n factorial mr over r to the n. And this is where m sub r is equal to this max absolute value of z equals r of that absolute value of f of z. And since this absolute value of f of z is less than or equal to 1 over 3 minus absolute value of z on the absolute value of z equals r, m sub r is less than or equal to 1 over 3 minus r. So absolute value here of that f to the n of 0 is less than or equal to n factorial over r to the n times the quantity 3 minus r. And to optimize this, we can minimize and r to the negative n, 3 minus r to the negative 1. Then equivalently, we're going to maximize r to the n, 3 minus r. We let g of r equal r to the n times 3 minus r. So g prime of r equals nr to the n minus 1 times 3 minus r to the n. That equals quantity r to the n minus 1 times this quantity 3n minus parentheses n plus 1 times r. So our critical point is r equals 3n over n plus 1. So from here, the best bound is going to be this modulus here, this f n of 0 less than or equal to n factorial over this denominator 3n over n plus 1 to the n times the quantity 3 minus 3n over n plus 1. And since 3 minus 3n over n plus 1 equals 3 over n plus 1, then we could say modulus that fn of 0 less than or equal to n factorial quantity n plus 1 over 3 to the n plus 1 n to the n. And some might acknowledge this as the nth derivative here, if you want to acknowledge it like that. So using 1 plus 1 over n to the n, asymptotic to e, then we have this modulus, this f the n of 0, the nth derivative, we could say is less than or asymptotically comparable to the following: e times n plus 1, n factorial divided by 3 to the n plus 1. Okay, so on to number 2. Let's see if this holds up. Let me just read this. Whoops. So number 2. Let me just get this in. Okay. So number 2, let f of z equal e to the 1 over z over z squared times the quantity z minus 1. So a, b, c, and d respectively. Determine the type of singularity at z equals 0. Part B, find the residue of f at z equals 0. Part C, find the residue of f at z equals 1. And part D, we're going to evaluate that integral. So this is Lorentz series and isolated singularities. So at z equals 0, we could say e to the 1 over z has an essential singularity. Multiplication by rational factors does not remove that essential singularity. So z equals 0 is an essential singularity. And then for part B, the residue here, to find the residue at 0, we're going to expand that 1 over z minus 1 equals negative 1 over 1 minus z, and that equals this negative sum from k equals 0 to infinity of z to the k, valid for absolute value of z is less than 1. And e to the 1 over z, that equals this sum from m equals 0 to infinity for 1 over m factorial z to the m. So f of z equals negative this sum from m equals 0 to infinity, that 1 over m factorial z to the m, times this sum k equals 0 to infinity of that z to the k times that z to the negative 2. So a typical term is going to be negative 1 over m factorial times z to the k minus m minus 2. And k minus m minus 2 equals negative 1. So k is going to equal m plus 1. And the residue of f at 0 here, that's going to equal this negative sum of m equals 0 to infinity for 1 over m factorial, which is going to come out to negative e. So our residue here is going to be negative e. Now for part C, we want the residue at z equals 1. So right down here, sorry about that. At z equals 1, the pole is simple, so this residue here, it's going to be this limit as z approaches 1, z minus 1, times e to the 1 over z divided by z squared times the quantity z minus 1. So that gives us positive e. So the residue here of f at 1 at equals e. And for part D, the contour is square root of z equals 2. The contour integral and encloses both 0 and 1. Therefore, for this f of z dz, that's going to equal, when we evaluate it, 2 pi I times negative e plus e equals 0. So we're just going to get 0 for letter D. Okay, so that is number 2. And moving along to number 3, let's see if this holds. Let me just change it. Sorry about that. Okay, so we want to evaluate this integral here from negative infinity to infinity, cosine of ax over x squared minus x squared plus 1 squared. Okay, so dx for a is greater than 0. We want to justify the contour choice and estimate the contribution from the large semicircle. So contour integration here, I know it's written a little differently. So I equals negative infinity to infinity cosine of ax over quantity x squared plus 1 squared dx, where a is greater than 0. So we're going to consider the integral negative infinity to infinity e to the iaz over z squared plus 1, that quantity squared, dz. Using the upper half because a is greater than 0, so this absolute value of e to the iaz, that equals e to the negative ai, the imaginary here, the set of that imaginary part of z. So negative a imaginary part of z, sorry about that. And that decays in the upper half plane. And the denominator factors as z squared plus 1 quantity. That's the quantity z squared plus 1 squared. That's going to equal z minus I squared times z plus I squared. And inside the upper half plane, there's a double pole at z equals I. So from there, we're going to let f of z equal e to the I a z over z plus I squared. And then from here, e to the I a z over z squared plus 1, that quantity squared, that equals f of z over z minus I squared. And the residue at the double pole is going to be that at that z equals residue sub c z equals I, that equals f prime of I. So f prime of z is going to equal IA, this is an e, sorry, IAE to the IAZ over z plus I, that quantity squared, minus 2e to the IAZ over the quantity z plus I cubed. And at z equals I, z plus I is 2I, so z plus I squared is going to be equal to negative 4. Z plus I cubed is equal to negative 8I. And e to the IAI equals e to the negative a. So f prime of I, that equals IA e to the negative a over negative 4 minus 2e to the negative a over negative 8I. And the first term is negative IA e to the negative I over 4. The second term is going to be e to the negative a over 4I. And that's going to equal negative I e to the negative a over 4. So f prime of I, that equals negative I e to the negative a over 4 times the quantity a plus 1. So going back to the integral, so if we write it as negative infinity to infinity e to the IAX over x squared plus 1 squared dx, evaluating that, that's going to be 2 pi I bracket negative I e to the negative a over 4 times the quantity a plus 1 close bracket. And hence here, this is equal to pi over 2 times the quantity a plus 1 e to the negative a. So just taking the real parts, the integral from negative infinity to infinity, cosine of ax over x squared plus 1, that quantity squared dx, that's going to be pi over 2 times the quantity a plus 1 times e to the negative a. So that's all for the third one. And that's all for part 1. Thank you very much and have a great day.